I'm Jeff Dean, and I lead Google Research, and I'm here to talk to you today about some of the exciting work that's happening in the intersection of using machine learning for computer systems problems at Google. I'll be presenting the work of many, many people at Google, and I'll attribute different subsections of this talk to particular groups of people. But I just want to say thank you very much for having me in the workshop, and I'm delighted to be giving this talk. I'm sorry I can't be there in person today, but here I am virtually. So I think there's tremendous opportunities for machine learning to improve computer systems. I think lots and lots of aspects of computer systems, some are just listed here in compilers and networking, OS operating systems, job scheduling, ASIC design, and so on, are all areas where they tend to use a lot of heuristics or sort of approximation algorithms to try to do something, and often learning can actually help tremendously improve this. So I've been saying this for a long time, and actually this is a slide from a 2018 talk in this workshop. And the way I've decided to structure the talk today is to give you updates on a lot of different work that we've done in these areas, progress that's happened, and really around these different sort of sub areas. So let's start with ASIC design, and in particular, a few different aspects of ASIC design. So there's a huge potential for machine learning to really improve the way we do modern hardware design. And I like to think of this as a long-term goal to how can we learn to design chips in days or weeks rather than the many, many months or even multiple years that it takes for doing that today. And this is the work of many people at Google that you see listed here. And really, deep learning is transforming the computers we design. So it makes sense that we should be thinking about how it might be able to transform how we design computers. And designing a new chip is currently really time consuming. It requires dozens to hundreds of person years of effort and really specialized kinds of expertise, actually many kinds of expertise. But what if designing a custom chip would take a few people just a few weeks? I think that's a really good aspirational goal to try to get to. And that would mean we would have much more specialized hardware than we have today, because the sort of investment you need to make to get specialized hardware is much, much smaller, and so on. And really, there are lots of time-consuming phases of chip design, but let's talk about a few of them. First is placement and routing, and we think, and I'll demonstrate that we can learn to quickly generate really high-quality placement and routing solutions. Verification is a very time-consuming phase, and we can actually use learning to automatically generate test coverage with some small set of tests. So we can expand the set of tests and cover things that we know we want to cover in a more automated way. And then I think architecture exploration and RTL synthesis are really interesting high-level aspects of chip design. Can we learn to automatically do architectural exploration and synthesis? And we've been starting with a restricted class of applications for now, but eventually want to expand that to broader sets. Okay, so let's talk about each one. First, placement and routing. Using reinforcement learning to quickly and automatically generate high-quality placement and routing solutions. So we've been doing work in this space for a little while. In 2020, we had an archive paper that we posted on using deep reinforcement learning for chip placement. And that eventually turned into a Nature paper on the general approach. And RL, as you obviously know, works really well for hard problems with clear rewards. So things like chess or game playing like Go, where you know you have you win or you lose, and you can sort of backpropagate that set of actions through that set of actions and understand the reward that you get for the different moves you made along the way to either winning or losing. So can we get an RL agent to successfully play the game of ASIC chip layout? One of my favorite games, coming soon to middle school children everywhere. And it turns out that this game is actually very complicated. It's got many more states than even the games of chess or Go. So it has a really broad search space. And many objectives also. Unlike just winning or losing, there's area considerations, timing, congestion, design rules that can't be violated, and so on. And the true reward function is very expensive to evaluate. It often takes many hours to run the design tools on a modern chip for just one particular hypothesized placement. And we'd like to have, iterations that use tens of thousands or maybe hundreds of thousands of potential placements to get a reinforcement learning algorithm to actually learn to do this. But you can formulate it as an RL problem with a RL agent that places macros or groups of logic cells. It's too expensive to place each individual logic cell, so we tend to group them and cluster them first, and then we get a small enough number that we can actually have an RL agent that deals with hundreds of different things on the chip and knows how they're connected. And we take a bit of a hybrid approach. So the RL agent is going to place these macros one at a time, and then we are going to use an analytical placer to place the standard cells after we've sort of left space for them and place large clusters of the standard cells, and then we let the standard design tools do that. Let's see. And so you can formulate your reward function so you incorporate these multiple factors like wire length and congestion and density. You can also incorporate other metrics like timing or shape constraints and so on. And then you have a graph convolutional network that looks at the sort of different pieces of the chip, the different modules, and also how they're connected, and gets edge embeddings and macro embeddings for each, and then uses those and feeds them through a policy value network that makes a decision about which macro or grouping are we going to place next and where. And so here you see the results on one of the design blocks within one of our TPU designs, the TPU chip, ML accelerator chip. The white blurred areas are these macros, and typically human experts will kind of put those around the edge of the block, and then you have your logic in the center, which needs to talk to the different macros. And the ML placer, as you can see on the right, finds smoother, kind of rounder macro placements that reduce the overall wire length. And so in this case, the time taken for the human design on the left was 6 to 8 person weeks. The ML placement on the right was only 24 hours. And the total wire length is actually better, and roughly the same number of design rule violations that would need to be fixed up by humans. More interestingly, can we train a general agent that is quickly effective at placing a new design it's never seen before? So when we first started doing work in the space, the way we would do this is we would take a particular chip netlist for a particular block of a chip, and we would iterate the reinforcement learning algorithm to eventually come up with the final result, and it would sort of get better and better at placing that particular block with tens of thousands of iterations. Now one of the things we do is we pre-train the policy on a bunch of different netlists, so a bunch of different chip blocks of various kinds, even across different chips, and then we can fine-tune them on new netlists. So tens of thousands of iterations to pre-train this policy. But then that's done once ahead of time, and then you get a new net list with a pre-trained policy, and then it only takes hundreds of iterations to actually get to a high-quality placement. And you can see that in this graph. If you take the approach on the left from the previous slide, the blue line there shows you what happens when you train the policy from scratch. It eventually, it has a pretty high cost initially, and eventually, after 20 hours or so, it drops pretty significantly and eventually converges to something, in this case, below 0.2 for this particular block. But if we used the fine-tuned pre-trained policy, what you can see is that you get to a very good placement much more quickly. And actually, interestingly, the circled area I'd like to highlight there, the zero time, the zero shot placement, you actually get a pretty good placement already. And I think that's going to be important for being able to use this in conjunction with things like high-level synthesis and so on of chips much higher upstream in the design process. And generalization results here, you can see that the commercial tools generally don't do as well as the approaches in the yellow bar here, which is from scratch or either fine-tuned for 12 hours, the darker blue ones. And then the zero-shot ones are even quite competitive with the commercial tools in some cases. So that's exciting. And here you can see the training policy from scratch takes a while to figure out that it's a good idea to leave this hole for the logic cells in the center, whereas the pre-trained policy already figures that out very quickly. But eventually, the from scratch approach does realize that it's a good idea to leave these holes in the center for the logic. And we've been using it. So, for example, we've done RL for 37 blocks of the TPU v5 chip design, and we've compared them to placement by human experts. And of those, 26 of the 37 have better quality of result, QR is a chip design term, than the human experts. 7 are roughly equal, and 4 were worse. And we've made some progress since the usage in the TPU v5 case. In particular, we've done a bunch of improvements and new techniques to handle crowded blocks, which were the 4 blocks where the human experts did better than the RL algorithm. And a much higher percentage of blocks give better quality results than human experts on later chips than the TPU v5 results I presented on the previous slide. And we've also open sourced this approach. We call it circuit training. And it's got a released distributed RL infrastructure and circuit environment used in the Nature paper. You can see the GitHub link there. The Nature paper's results have been independently validated and reproduced by the TensorFlow agents team that produced the open source release, and Andrew Kang's lab is a strong chip design research group, and they've also reproduced the results. And the OS open source system is deployed in our production chip placements for our latest generation TPU. Let's see. And it's also enabled external research. So there's some nice external work by academic groups using this paper for follow-on work. So the benefits of this ML-based placement are really that it allows ASIC designers to quickly generate many alternatives, different trade-offs, tackle the most complicated blocks. It can quickly redo the layout, even if there are major changes in design upstream. One of the reasons designs get frozen very quickly in chip design is because of the placement aspects being so labor intensive and so long to redo them that you can't really make major design changes without really affecting that. So this can significantly reduce the time and effort to develop new ASICs by using RL-based placement, and accelerates innovation and design across the chip design field. Okay, verification, another time-consuming phase of chip design. Can we learn to automatically generate test coverage with a small set of tests? And it's verification is actually one of the biggest bottlenecks in chip design. Typical estimates say 80% of the effort is in verification and 20% in design. And a fundamental question is one of reachability analysis. Can we reach particular states in the system? So can we learn a continuous representation of a particular chip design that allows us to predict its reachability? That would help us with answering different kinds of verification questions. And so can we use machine learning to generate test cases that exercise more of the state space in much less time than the state of practice? And this was a paper that appeared in last year's NeurIPS by the authors you see there, learning semantic representations to verify hardware design. And the basic approach is you have the RTL of the chip, which is kind of the source code description of how all the different pieces of the chip are connected. And that you can view as some RTL-like language, or you can view it as a data flow graph and data edges and control edges. And that gives you an abstract representation of the hardware design. So the question is, can we actually, use deep learning to learn a continuous representation that can predict answers to these state reachability queries? And more importantly, can we actually scale this to real-world size designs? Since that's ultimately what we care about. And really, the approach used is to take input like this and then to learn dense representations of all the different components of the chip in a graph-based graph neural network that we can then use to predict various properties of the design. And the properties we want to predict are, we want to, for example, predict coverage for different tests. So here are a bunch of things we might want to cover in the columns, and different tests that cover different states in the chip. And you can view this as supervised training data. So we can say that, okay, this particular test with the source code for the test covers these 4 cover points, C1, C2, C4, and C5. So then if we have a new cover point that we want to cover, which tests might cover it already? And if we have a new test, can we predict which cover points which will actually be covered by that test? And so for a new test and an uncovered cover point, we only care about uncovered cover points since the covered ones are already tested. Can we predict if the test can cover the cover point? And so it turns out that if you have a baseline approach that doesn't get to know the details of the design, but only gets to see the coverage and test information, then you don't do very well. But if you enable the system, design to fact, to see the RTL design and actually have sort of dense representations of the components of the chip, it can actually do a much better job and does better across 90% of cover points, 80% of cover points, and 50% of cover points for the training set size. And this is results on a commercial design, a TPU chip, where we actually have a few different baselines, and design to fact improves on all the different baselines in predicting what parts of a design a test can cover. Again, transfer learning across different versions of a design is something that was demonstrated in the paper. Okay, so the impact of this would be that verification is a long-standing big problem in chip design, and that it takes 100 people 18 months or so for a particular fairly complex chip. And this deep representation learning can actually improve verification efficiency and quality beyond the state of practice and state of the art. And it can generalize across designs for test generation. So that has the potential of saving many, many years per different generation of chip designs. Okay, and then let's look at the highest level of chip design that we've been looking at, which is how do you explore different potential chip architectures and then do RTL synthesis for those architectures. And one of the things we've been looking at is restricting our search to just how could we create an accelerator chip for a particular neural network architecture, since that seems like an important area for speeding up computation now and in the future. That's the domain we've been restricting ourselves to. This is not arbitrary chip to do all kinds of things like a modern CPU or a compression chip or something. This is just for neural network accelerators. And there's an archive version and then a more recent ASPLOS version, as you see here, of the section that I'm going to describe. You can refer to these papers for more details. So one of the issues that happens with chip design is that the model development and improvement in models outpaces chip development. So if you look at just kind of image-based models, in 2012 there was AlexNet, in 2014 there was VGG16, then ResNet, and so on. And you see a substantial, improvement in accuracy through improvements in the architectures. Many of these models have substantial increases in the number of floating point operations to do an inference relative to the earlier years on the slide. And really, it's kind of a moving target. Hardware accelerators take about 2 years to develop and then are deployed for 3 years. And so you tend to optimize for what you think are the popular workloads at the time of development, or maybe some forward-looking sense of what do you think is going to be important in the 2-year time frame, but it's often very hard to predict this. So if the design cycle can be reduced, then single workload accelerators can kind of become viable. Gives you this nice positive feedback loop, enabling faster evolution of AI models because now you can accelerate them, and so on. Oops. And so we use ML to extend the design space exploration. Typically, design space thinks about the data path, but we actually can simultaneously optimize the data path, the schedule, and compiler decisions, which gives a much larger search space, but is much more effective than just trying to think about the data path without what are the downstream effects of making a compiler that takes advantage of decisions in that data path. Yeah, so one of the things you feed in are power and area constraints into a black box optimizer, and then neural network models. And then you feed that into a simulator of sort of alternative computer architecture designs for TPU-like chips or ML accelerator-like chips. And that then gives you an end-to-end performance and power estimate of that particular architectural design and how it would perform for this particular model. And there you see some of the kinds of things that are in the search space. It's things like how wide and how high should you make your matrix multiply unit? How big should the vector unit size be? How much cache memory of various kinds should you have? How many DDR channels should you have to memory? And so on. And so what I'm going to show is a series of graphs that compare the search in the green for a single workload, so a particular kind of neural network, relative to a TPU v3 baseline in blue. And then red is going to be a TPU v3 baseline plus some of the compiler optimizations that were discovered as part of the green search, but not changing any of the architecture. And so what you see is you get some benefit from new and interesting compiler optimizations that have been discovered, but there's still substantial headroom that comes from jointly co-designing the hardware architecture decisions and the compiler fusing optimizations. And so you typically get a perf per total power, TDP is total power, improvement of 3 to 6x over the baseline TPU v3. And TPU v3 here, I should point out, is a hypothetical TPU v3 that's been die shrunk to the same sub 10 nanometer process. And in this case, the 7 different models are all fairly similar. They're efficient net sizes B0 through B7, which are different sizes of computer vision models. But it's interesting that custom designing them for particular sizes actually is pretty effective. But what about other kinds of models? So in this case, you can extend this search process and look at behavior for other kinds of models like ResNet or BERT. So it's bringing in some of the transformer-like natural language processing models. And you see a geometric mean over all these kinds of models above 3 improvement over the baseline hardware. What about instead of just customizing for any one particular model, what if we customize for a collection of them? And so in this case, we're going to customize a chip for all 5 of these models, EfficientNet V7, ResNet 50, a couple of OCR models, and BERT 1024. And then what you see is you get this nice geometric mean speed up of the 5. So you get a pretty good speed up for the 5 different chips there. And you get a hardware design that can actually run all 5 of those models effectively. Okay, and if you look at performance, instead of performance per watt, the speedups are actually even higher. So being able to easily customize and optimize for specific workloads instead of building more general purpose devices can lead to pretty significant improvements. And with the kind of trend of having certain kinds of models that we care deeply about for inference purposes, for example, this seems like it's going to be an important general trend. Okay, so opportunities for learning abound. I hope I've, at least in the hardware design space, and I've covered a bunch of different areas there. If we apply them in all the right places, could we actually get to the point where learning plus ML computation allow a handful of people to use those ML tools to design a chip in a few days or weeks? And it seems plausible, we could be on a path to do that. We've published a bunch of work, so I will not go over any of this in detail, but these are some references that you might be interested in. Okay. Another question is, how can we easily embed learning into existing computer software systems in particular? We want systems that can optimize themselves automatically, but a lot of existing computer systems are very large and complex. Things like compilers and operating systems and networking stacks, and they have hundreds of millions of lines of code that already exist. So we want something that can easily integrate into this code with fairly minimal changes, but can then use learning in the right places. And we're building a system, an API called Smart Choices that allows this. This is actually a slide from the 2018 talk in the workshop. And so now I can actually tell you more about Smart Choices and the fact that it now exists and has been used for a bunch of interesting things that I will tell you about. So this was a motivating example of why we wanted to build something like Smart Choices. So if you think about Bigtable, which is a large distributed storage system, it has a bunch of clients, it has a bunch of tablet servers, and it has a bunch of chunk servers in the distributed file system. And one of the things the tablet servers have is a cache. And so you have the client, the tablet server, and the chunk server. And it has an in-memory block cache of blocks so that we can not have to go all the way to the distributed file system if it's already in the in-memory block cache. And so there's some code that looks something like this. If we should insert it into the cache, then we insert it. Now, there's a bunch of contextual information available here that would make sense to consider if should we insert this particular block into the cache. Maybe the job name of the client job would be an interesting thing that would be useful to know if this block is likely to be reused or not. So we could implement should insert, and then we might be able to say if the job name starts with MR dash, indicating it's a MapReduce operation over a bunch of data, then maybe we shouldn't cache it. And so we could say if the job name starts with MR dash, which is a common convention for MapReduce jobs within Google, return false. But you would never actually want to write that code in your, the core of your computer system. Things that depend on like particular job names and have very different behavior when there's one job name versus another. But you could imagine a learned should insert operation that takes a bunch of contextual information that's available, maybe the job name, or the username, or the table name, some other things, and makes a decision about whether to insert the block. And so that might look like return inference on some complicated machine learning model that returns either true or false about whether that particular block should be inserted based on some of these input features like job name, username, table name, and so on. And so the Smart Choices API sketch is really a choice, which is a hook that application code calls to make a decision. And then one of the key things that enables learning is feedback. So application code can report some sort of reward, either positive or negative feedback, when some metrics become available. And then a session ties together choices with the corresponding metric feedback, and context is information that might be useful for making a choice inside a session. And so here you can see, choose, and then later you can give feedback. And then there's an in-memory buffer of choices and feedbacks, and then you can periodically train it and update a serving model that then affects how subsequent choose calls behave. Now, one of the interesting things is you don't always get feedback in the same process or even the same computer as the one where you made the choice. And so we need to be able to handle choosing in one process and then a much deferred kind of feedback later. That all works. There's lots of variations. You can do this, sample, periodic training. You can distill the model to make it really lightweight, and so on. A few lessons that have been learned in using Smart Choices in various places. First, minimizing dependencies is really important for some really low-level systems. So if you're making choices about, say OS process scheduling, you don't want to bring in a whole machine learning model compiler system into that kind of lightweight usage. And so we have a very lightweight C++ library for doing Thompson sampling, for example. We also have a full-blown online XLA-based ML compiler runtime for more sophisticated models. And it must be really easy to automate and retrain the heuristics as things change. One model that was frozen for a while and not retrained made a choice of how many threads to use for a request in Google Flights based on request characteristics. And this, when it was initially rolled out, worked great. It had a major effect on reducing latency and improving, total system throughput and so on, because it chose the right number of threads based on how expensive it could predict the request would be. But things change. So over time, as the Google Flight system, started to run on new CPU types in different data centers, or there were changes in the overall code to make, certain things more expensive or less, that can turn good choices for how many threads to use into bad ones if you don't update the learned decision. And so we've been really erring on the side of generally trying to have fairly online retraining of heuristics rather than freezing them forever. Another couple of lessons is, smart choices can be used for lots of different things. One is making choices in computer systems. The other is in sort of making UI decisions, like how big should this font be, or should we show this tip to the user or this other tip, and so on. And one observation the Smart Choices team has about how people are using their system is that systems optimization problems tend to care less about explainability. If kind of the underlying metrics that are being optimized, like latency or CPU cost or whatever, move in the right directions, the next questions are more about, how complicated is this going to be, and how about maintaining my system with this now learned choice. Whereas UI selection problems, sometimes the users of the system for that care a lot about explainability. Why are these websites or users getting treated in one way or another matters more than why did the compiler choose a tile size for a shape in a more system-y setting. So here's a few kinds of examples of problems to which smart choices have been applied. How many threads should I use for this request is one I mentioned already. Should I drop this request? What's the best notification string for this user? Which 3 out of 49 actions should we show? So those last couple are more UI focused. What tile size should I use to move this memory? Should I split this request into smaller pieces? And which cache item should I evict? So motivated by the cache insertion question, it's actually been used for cache eviction questions, and I'll talk through that now. And in particular, this is kind of at the intersection of networking and operating systems, and that is YouTube caching and placement in our global YouTube serving network. So YouTube has lots and lots of caches of frequently viewed content with roughly 1,000 points of presence all over the world. And replacing the existing heuristic cache replacement algorithm with a new hybrid algorithm. So heuristic, something like LRU or something like it, selects a bunch of candidates. And then the learned algorithm does pairwise comparisons among these n to try to identify which candidate to evict. It's trying to predict which one of these pairs is least likely to be reused soon. And what you can see here is like the existing system on the left up to day 7, and then where the dotted line occurred, there's a rollout of this new learned cache replacement algorithm. And you can see the normalized byte miss ratio dropping substantially. And this is a pretty big deal because network bandwidth and byte misses in the different points of presence caches matters a lot. And this improves the byte miss ratio at peak by about 9%. And there's a manuscript in preparation that's not available yet describing this work in much, much more detail. Learned index structures is another interesting area where machine learning can be used to improve computer systems. And this is work where data structures that can learn from and take advantage of the actual distribution of data can be better than conventional kind of distribution of oblivious data structures. So algorithms like B-trees and so on don't have any knowledge of the distribution of the data in the system. Whereas if we actually know the distribution because we are kind of learning as we go, we can actually do significantly better. And so B trees you can think of as being kind of models. You have a key, and the B tree is trying to get you to the right page where the key should exist if it does exist. And the conventional B tree lookup algorithm actually does get you deterministically to the right page, and then you can look at it. But you can think about a learned index, which is a model that's going to take in a key, and it's going to try to predict the position in the sort of total ordering of key space in order to predict where that key should be if it actually exists in the data structure. And so what the learned index does is it tries to train one of these models to best predict the position of that key, of any given key in the space. You can think of this as trying to predict the position in the cumulative distribution function of the key space. And this is work from published in 2018, where we showed that it actually works substantially better than a B tree. So if you can make different kinds of trade-offs depending on the sizes of the model, but 60% faster at 1/20th the space as the conventional B tree, or 17% faster at 1/100th the space. So that's pretty dramatic improvements, and really can sort of rethink what having an index means in your database system or whatever, because all of a sudden the trade-offs in terms of space and performance change dramatically. And this has many more uses. I'm not going to go into them today. Also works for things like hash tables and Bloom filters and sorting algorithms and so on. Okay, I will quickly touch on job scheduling systems, which tasks and VMs to co-locate on the same machine. This is another smart choices example. In this case, there's a work scheduling system at Google which can choose to either execute a work item or split it into smaller work items that then get executed. So if you, the complexity of this choice is that work items that are too large can experience timeouts and therefore give an error. But splitting work items too finely can increase system overhead and kind of overload the system in other ways. So you can use smart choices actually to make a decision of whether to split or execute a particular piece of work based on information about the task and about the system state. And one of the outcomes of this was that there was a reduction of 78% in error rate, but with no increase in system overhead. So basically the system was learning just the right level of splitting to avoid errors, but not to oversplit which would increase system overhead. And that's some unpublished work, but just a flavor of the kinds of things that you can use learning for in the middle of computer systems. Okay, compilers is another exciting area. And you can apply this to traditional compiler problems. And let's talk about inlining. This is actually a topic near and dear to my heart. So you can see the kind of low resolution PostScript screenshot of this paper that I worked on with my PhD advisor as one of the first papers I worked on in grad school. It was published in Lisp and Functional Programming in 1994. And this was an approach that didn't really use learning except in the sense of trying to generalize. You can think of it as a very simple kind of learned model where it's trying to make automatic decisions about whether a particular routine is profitable to inline based on the way in which static information available at the call site was exploited during compilation. And you want to try to generalize that. So if you look at what this was doing, you suppose you have a thing called myfunction that has a bunch of call sites. And at one call site, it's called with two constants. And the second call site, it's called with some variable that is an unknown value and 17. And in the third call site, it's called with two things where the value is not known at compile time. And so the hope would be that inlining trial is a way and you can perform compilation and then the optimization process on the inlined code. And you can record the most general sets of types that would enable key optimizations. And this is where trying to enable generalization is why you're doing that. You want to be able to say, if for example, learn that my function, when called with a constant and a constant greater than 0, has a code size of 1 and an estimated runtime of just 1. But if you call my function with not a constant and a constant, then the code size is larger because it wasn't able to perform as many optimizations, and the estimated runtime is 2. And if you call it with two things that are not constants, then the code size is actually quite large, and the estimated runtime is also quite large. So this is kind of a learned approach, but not using sort of traditional machine learning algorithms. It's just really trying to track what optimizations were done and then create the most general set of types that would enable those kinds of optimizations. But some Google colleagues in 2022 published a paper that uses reinforcement learning for inlining decisions in LLVM. So this is really the culmination of actually doing the right thing, which is using true machine learning in order to optimize for inlining decisions. This actually replaces the heuristic-based inlining for size optimization, LLVM, with a machine learning model. It's available in the main LLVM repository. It's trained using policy gradient evolutionary strategies and achieves up to 7% size reductions versus the state-of-the-art LLVM optimized for size flag. And it also generalizes to new binary targets, as well as continuing to work well on the same targets, even when you have many months of active development. So this is pretty neat. It's great to see sort of RL applied to this problem. ML computation. So there's a lot of problems in ML compilers that are really interesting. So some of my colleagues published a paper that tried to do auto-tuning for the XLA compiler that maps ML computations expressed in TensorFlow or JAX down onto the actual TPU chips and makes decisions about lots of different things. So things like layout assignment or operator fusion, also makes decisions about tiling and compilation flags that are going to give the best performance. And so the blue things on the left are optimizations that are tuned, so layouts, operator fusion, tiling, and flags. And then the yellow are two different learned models that help make these kinds of decisions in the middle of the compiler. And what you see is that you get, they measured 150 ML models, you get greater than 10% speed up on 20 models. The largest improvement was 2.4x on a particular speech-related model. And you can see some of them benefit a lot from fusion, which is green. Some benefit a lot from choosing the tile size better, which is the yellow, and so on. So it's really important to be able to learn all these kinds of different things in order to get the best performance. Okay, so I've got a box around all of these because I think I hope I've demonstrated at least some aspects of being able to learn interesting things in the middle of computer systems that affect all of these different kinds of areas. And I think this is a general trend. This is by no means the full set of things in which machine learning for computer systems can be applied. But I think people should be looking for more and more opportunities to really do this in more places because it's actually working in many, many problems that we look at. And so I think it should be really changing how we think of computing, and in particular computer systems are ripe for rethinking around some of these learning-based approaches. And we're seeing success in a lot of different areas. Can we rethink even more of the status quo in computer systems using learning-based approaches? And I believe the answer is yes, but I'd love to talk to you about it. And thank you very much for listening to my virtual presentation. Thank you.
Awesome. Thanks for the great talk. So we have a live audience here, and we'll have live questions as well. So if you would like to ask a question, please come to the front. We have a microphone.
Carsten Binnig, TU Darmstadt. Thanks for the great overview that you gave. So I was wondering, in the first part of your talk, you presented an idea of zero-shot learning, which is maybe, my take on it is we learned the basic principles of learning computer science design problems. And so we've done a similar work on database optimizers, so query optimizers. But the question is, I was wondering, so how general is this principle? So to which system components do you think this zero-shot idea translates to, and where should it be applied?
It's a really good observation. I think it is actually pretty broadly applicable, because I think in a lot of cases there's some general sort of set of domain knowledge or expertise that is applicable to a wide variety of different kinds of similar problems, and you get a lot of benefit from learning a model that kind of sees many different examples of a particular class of problem and then can generalize to new ones. And then you get, further benefit from, detailed study of a particular problem, in the case of chip design, like the particular chip design, as opposed to having, done a bunch of other chip designs. But I do think the ability to make those quick, zero-shot assessments of quality of a solution is a really helpful thing for downstream things. Like you can imagine the compiler optimization work, you have some new function you've never seen before, but you sort of have seen a bunch of functions that are kind of similar in shape and size and structure, and you can make very quick decisions about whether that's a good thing to inline or not, based on your knowledge of other ones.
He says thanks. I have a second question.
Great.
My name is Saurabh Adya from Apple, and the question is around circuit placement. So there has been some, it's great work, this whole concept of applying learning to the chip design problems. There has been some reproducibility problems with that work. I know Andrew Kang's lab is trying to reproduce that. They've reproduced the flow, but according to the latest update, they still haven't reproduced better results from RL. It seems like the traditional industry tools are better, according to their designs, right? So then the ask is, can we release new benchmarks or even produce results on existing academic benchmarks to be able to see if, apples to apples, how it performs compared to traditional approaches?
The essence of the question was about reproducibility of the results, and that's why we open source the sort of RL-based chip placement. And certainly, like additional benchmarks in the industry, I think would be a really helpful thing. We could all, benefit from more ways to evaluate these sorts of systems. So, I would say, external people can reproduce the results from the Nature paper, at least on the public designs. Obviously, they can't do it on our proprietary TPU designs, but that's because we are not willing to release the actual chip designs for our own chips.
Hello, really nice talk. My name is Dan Grubisic, coming from Rice University, and I would like to hear your opinion about optimizing runtime. We saw in research a lot of work in optimizing code size, which is something we can do. We can download GitHub code without compiling it. I mean, we can compile it and optimize code size, but for runtime, you actually need to build it and execute for a particular machine. And the problem is machine learning often requires a lot of data. So what do you think is going to be a good approach for optimizing speed and maybe power consumption for codes with machine learning? Thank you.
Yeah, I caught that the question was about how do we actually evaluate the runtime benefits of different optimizations rather than just code size, which is easier to measure. Completely agree. I mean, I think this is a problem that all compiler optimizations really have. They're trying to predict, what will the effect be on the actual running performance of the code, and often you don't know lots of attributes about the code, like how many times will this loop run, exactly what architecture you're going to be running it on, what are the other kinds of processes on the system that might be interfering with your cache usage and so on. So, I mean, I think there's some answers to that, which are to sort of build more detailed machine models and use kind of very small scale pieces of code that you could imagine having a ML-based prediction of how fast a given, say, piece of code would run, and building up sort of larger scale predictions from a bunch of zero-shot predictions of that. I do think anything we can do to model, and make quick estimates of how fast a particular version of code will run, sort of like the zero-shot for chip placement, will help us upstream, because it will enable us to have more informed decisions in the higher level optimizations we're making about what the effects at the lower level will be.
So we have one question on the chat as well. This is by Joshua Newnham. Is there a risk of ML models in systems introducing rare behaviors or edge cases leading to operational or firefighting problems. Is this something you're able to plan for and de-risk?
Yeah, I mean, I think there are some classes of ML for systems problems where you do care a lot about interpretability. Probably like when you're getting paged and in the middle of the night and the system is making some weird decision, that would be a case where you really want to understand why is the system behaving in the way that it is. I think there are other ones where interpretability is less important, but it does mean that we should kind of strive for systems that are easily understandable by people trying to debug or make other improvements to the system. And I think the whole litany of literature on ML interpretability is very relevant here. You know, we can use interpretability methods for all kinds of ML for computer system problems, in addition to kind of more traditional ML for, you know, image classification or other kinds of ML problems. I do think ML systems can be actually better in a lot of respects in adapting to the changing circumstances. So if you have an online system and the ML system is making decisions, you often want to be able to react to the live flow of updates to the system and make good decisions given the context. And that sometimes kind of heuristic-based systems don't actually do that as well as the learned systems. But better interpretability is certainly handy and useful.
Riyad Baghdadi, NYU. So thanks a lot for the very interesting talk. My question is, to what extent, or I think during your presentation you said that many of the systems are used in production, but like to what extent, so I work on using ML for compilers, for compiler optimizations. And one of the worries is how can we make this general to production systems? So in your experience, to what extent are all of these systems that you presented applicable in production systems and on real world problems? Are all of them, or is this difficulty that you are seeing?
Yeah, I mean, I think the transition of using ML in the middle of core computer systems is kind of, in my view, just starting really for most computer systems, right? People are starting to experiment with it in some particular subproblems within different systems. The compiler work that I showed you that my Google colleagues actually put into the LLVM release for the inlining for size heuristics is a good example of a production sort of system that actually is using ML to make real world decisions. The placement and chip design stuff that we're using is in production for our chip design teams. And then other stuff is a little more exploratory and early stage. But I think this is a transition that is happening and will continue to happen more and more as we have kind of more and more complex systems, and we really want to use learning to take into account the full context in which decisions are being made and to make kind of better decisions in a wide variety of things. And I think there's, dozens and dozens of opportunities in compilers alone that, we've probably started to explore a few of them, but not nearly all of them.
Thank you for having me. I'm going to talk about kind of a few broad topic areas we've been investigating in the area of how can we use ML for computer systems. And this is the work of many, many people at Google, some of which I'm a collaborator on, some of which I just think is cool and I think you should learn about. But the fundamental premise is that traditional systems code, things like operating systems, compilers, storage systems, really don't make very much use of machine learning today. And there's a real opportunity there to have these systems be much more adaptive, to be able to learn in an online manner from the sets of observations they're getting about the world to make better decisions, rather than what they are today, which is generally handwritten heuristics by the developer of that system that generally has to work in all cases or work pretty well in the average case and can't really customize to the names of files you're creating in your file system. That wouldn't necessarily make sense, but that might actually be something that a system could learn to do and learn interesting policy based on that. So I'm going to give 3 examples So one is sort of a progression of work we've been doing in how do you do automated device placement where you spread the computation out of a machine learning model across many different devices. And then kind of if you squint at that problem right and imagine now you're trying to place on the surface area of an ASIC wafer, that sort of leads to the second thing I'll talk about. And then the third is how can we actually make ML to be, if you want to deploy learning in machine learning systems, in sort of traditional systems, how can you make that as easy as possible? Okay, so machine learning for device placement of ML models. We've been doing work in this space for a little while. For large models, things where the model doesn't fit necessarily on one single device. You know, often if you're doing data parallel training and your model fits on a single device, it's relatively straightforward to make n copies of your model on n devices, broadcast the parameters out, do data parallelism style computation. But for many kinds of things, model parallelism can give you, the ability to train much larger models that are spread out over 100 devices or 10 devices or something. And the communication patterns are not as straightforward as a data parallel setup. So getting good performance given a lot of computing devices and some model expression of the model computation you want to do is non-trivial and not necessarily obvious how to do that best. So yeah, I think I said most of that. There's some examples of complicated models where you might want model parallelism to come into play with lots and lots of devices, lots of parameters, and it's not necessarily obvious which devices should do which parts of those computations. So you can pose device placement as an RL problem, and in particular, you have some model you want to run, typically over and over. So you want to run each step, and you're going to do many, many steps of the computation. You have some set of available devices, which might involve, a bunch of CPU cores, a bunch of different GPU devices, perhaps, or maybe TPUs, and then you can essentially have a policy, take that graph, place different pieces of that computational graph on different devices, and then make the assignment, and then evaluate the runtime by running a step of this computation and seeing how fast that performs. And if you iterate that and get feedback as an RL signal of how fast this particular placement ran, you can then essentially learn to do better and better placements through many iterations of this RL learning algorithm. And it'll actually learn some sort of non-intuitive placements. So this is in 2017, we did some early work in this, and this is a sort of language model, machine translation style encoder-decoder model where we had 4 GPU cards and the host CPU. And what you can see is that this LSTM that was unrolled in time, the kind of straightforward human expert placement would be to just place each layer on a different GPU card and then pipeline the computation forward in time. But the RL system is actually able to find some pretty interesting interleavings of how to map computation onto these devices. So it actually will occasionally use the CPU, which is much slower than the GPU, so it uses it every so often, but not all the time. So that was kind of the first bit of work we did in this space. And then in 2018, we wanted to scale that to larger models with more nodes in the computational graph. And so there was some additional work to do sort of essentially online clustering and placement of the clusters rather than placing each individual node. And that enabled us to scale to 80,000-ish node computation graphs and get pretty good placement results. And in particular, this hierarchical planning approach actually got the best performance compared to human experts for 5 of the 6 benchmarks we looked at and was pretty close for the other one. And then in 2019, there was some additional follow-on work by others that essentially was trying to train a single placement model. Rather than starting the placement model from randomly initialized parameters, you want to train the model to do placement of a lot of different kinds of computational graphs so that when you see a new computational graph, you can actually get into a good state for that computational graph very quickly because it's seen lots of kinds of ML computation-y patterns and how to actually put those on different devices. Why is that? Sorry, I don't know why my... No? Okay, well, we will give up on presenting that, getting rid of the bar. Okay, so here the objective is to minimize the runtime for a whole bunch of different graphs, including a distribution of graphs that the model has not encountered before. And so you have graphs from some target distribution of computational graphs, you have device placements, and you have some reward function. A reward function that the authors found to work reasonably well was the negative square root of the runtime of the graph. So you penalize it a little bit if it's not the absolute best, but more and more if it's pretty farly diverged from the best time you've seen. And one of the things that is important is to be able to build up some representation of the graph again. And so this work builds on this graph stage work by William Hamilton, Rex Ying, and Yuri Leskovec that builds a representation of graphs that gives you an embedding for each node, and then that feeds into a model that can then give you a probability distribution over devices for each of the nodes in the graph. And then you can sort of quickly make a placement decision. Okay, so that's all working reasonably well, and in particular, the generalization properties of this latest evolution of the work are pretty nice in that you can take so if you compare in this graph, runtime is on the y-axis, and we have a whole bunch of different kinds of models. What you see is that the human expert is the kind of second to the right bar in each group, and if you individually train the method just on that graph, you generally can get quite good results. But if you do this approach and then do fine-tuning on that graph, which is generally much faster than doing the full iterative approach just on that graph many times, you can get pretty close to the hierarchical approach and the individual training approach. So that's pretty nice. It's 16% better than human expert on average across a bunch of graphs and 9% better. But the search is the real benefit here because it generalizes very quickly and you get 15 times faster sort of accurate placements. Okay, so this then led on to, does one of these make this thing go away? Exit? Oh, exit? I don't think exit's the thing. I think, I see, it's hung trying to load the last little bit of my slide. We'll see what happens when I get to the conclusion slide. Okay, anyway, this is follow-on work by a bunch of people, and in particular, Anna Goldie and Azalea Meher-Hazeni have been the research leads, and Zhou Jiang and Mustafa Yazgan have been the engineering leads for this, but there's a bunch of people collaborating, including myself, on how can we then take the ideas that we sort of started to explore in device placement and then use them for a related problem of ASIC chip design and placement. ASIC placement and routing. And so we've seen in the last few years that reinforcement learning works well, even for very hard problems, when you have a nice, clear reward signal. And so we've seen, for example, the game of Go, which has a quite large number of states, be able to be essentially solved to superhuman levels with an RL algorithm incorporated into the search process of what gameplay makes the most sense. And so the question we wanted to ask was, can we get an RL agent to successfully play the game of everyone's favorite game, ASIC chip layout? Yes, let's all play it at home. And it turns out this is a super hard problem because the state space of chip design for a reasonable sized chip is actually really big, like 10 to the 9,000th. You don't normally talk about numbers like that. And so how can we actually effectively make these systems able to do placement of something with that large a state space? So there's a bunch of complexities. First, the problem size is really big. There's generally millions or even billions of items on a real-world chip that you need to be able to place in a way such that you have multiple objectives you're trying to satisfy. You're trying to minimize the total area that the chip requires because that directly influences the manufacturing cost of the chip and also your yield. You have things like the timing, the way in which you put these two things. If they're close enough together, that means the timing will be fine. But if you spread these two particular things too far apart, then the timing characteristics of the chip may not meet the goals you have for the overall chip clock rate. Things like congestion, you can put, with multiple layers, you can put some stuff on top of each other, but only up to a certain level. And then there's a whole bunch of design rules for each manufacturing process that you need to be able to respect to make sure that your chip is actually manufacturable, or maybe with slight tweaks by a human at the end is manufacturable. And the true reward function, which is generally the output of one of these electronic design software tools, given the input, is really, really expensive. They generally take on the order of hours or sometimes overnight to run and evaluate, how to do this placement. And so that makes it very hard for RL, because if your RL, reward evaluation takes 24 hours, that's generally not good if you need to run lots and lots of iterations. So the basic architecture we've been using is essentially to take something that has got a mask of the density of things we've placed so far. It's got an image of partial placements as well, in case that's useful. It's got some feature matrices of adjacency matrix for the various pieces of the graph that we've already clustered, so we don't place each individual sort of gate. We instead cluster things together that we know actually need to be really close together, and then try to place those clusters so that the things that are not necessarily quite so tightly coupled are the things we're really making decisions about where should those things be relative to each other on the surface of the chip. And then a node embedding for each of the nodes in the graph. And so here are the results that we've gotten on one example. So this is a low power ML accelerator chip. We've obscured some parts of the chip for confidentiality, but the human expert placement that took many weeks to devise is on the left, and you can see the characteristics of the ML placement are a bit different. It's sort of a bit rounder. Generally, humans like to have these kind of fairly regular parts of the chip that they put most of the logic of the chip in, and then the parts around that are going to be macros that are things like SRAM cells to hold memory, things like caches. And generally, you kind of segregate the way you do the placement into the logic-y part and then the macro-y part all around it, connected together in the right ways. And the ML placer is doing something similar, but it's got a bit more kind of rounded structure, so it has a little bit different surface area characteristics of where the logic and the macros interact. And if I could get rid of this, then what you would see is the results are pretty good. In particular, the proxy wire length. So one of the things that's really made this possible is to have a proxy reward function that you can evaluate very quickly on a partial placement or a full placement, so that you can evaluate that in a matter of half a second or a second instead of 24 hours. And that makes the RL feasible on this kind of problem. And so here you can see the results for a few different blocks. And in particular, there's a couple of things you look at. One is the area of the chip. The right-hand column is probably the most important. And then the other is the timing characteristics of the chip. So the worst negative slack is like, what's the worst timing characteristic of any particular edge in the graph? And then the total negative slack is the sum of all those across all the different connections in the chip. And generally what we see is that we can get comparable or even better than human expert placement results on this set of problems. And here's the results on a TPU design block. The white blurred areas are the macros, and again, the green area is kind of the logic in the chip. And what you see is, again, the relative shape of the way in which the logic is placed on the chip varies a bit by the human expert and the ML placers. And in particular, the time taken for the human expert for this particular block was between 6 and 8 person weeks. And the time taken for the ML placement was about 24 hours. And the total wire length is, a bit shorter. So this is pretty nice. Often the human expert is basically doing multiple iterations through this 24-hour kind of CAD tool turnaround time in order to actually do that placement over the period of 6 to 8 weeks. And essentially the ML placer is playing the game of ASIC placement with this proxy reward function that seems to actually end up being close to the true reward function. Ruh-roh. Oh, it's a nice animation. But, oh, there we go. Huzzah. Okay, so here you can see on the left, these blocks represent the macros. Everything else is going to be the logic. And when you train the policy from scratch, you essentially start from random placements. And so the system does eventually figure out that it should have this cluster of logic in sort of one cohesive region in the chip, generally in the center. But it does take a little while to figure that out during the process. You can see now it's starting to figure it out. Whereas what we've done, again, similar to the device placement, the latest device placement work, is we've trained a model on placing a bunch of other blocks and other chips. And so when you give it a new chip, it actually already starts with a fairly good idea that this is just a generally good idea for chips. You should put all your logic in the center and put all the macros around the edge. And it gets into a good state much more quickly than if you start from scratch without any knowledge about chip placement. And so here you see the placement results of the pre-trained policy with zero shot, which is already sort of pretty good. It's already got the characteristic of the logic in the center and the macros around the edge. And if you fine tune on this particular block with these particular circuits and connections and macros, then you get better results. Let me see. I think there is a graph that got skipped. That's okay. So the potential benefits here are, one is this system can allow ASIC designers to really generate a bunch of different alternatives that have different characteristics in terms of area and timing and so on, with relatively little sort of elapsed total time. So if you can explore the space of like, how will my timing be affected if I make the chip a little bit bigger, a little bit smaller? And this might significantly reduce the time needed to develop new ASICs as a sort of new tool in the toolbox of ASIC designers. Okay, the last thing I want to talk about is simplifying machine learning in existing systems. And our software systems have lots and lots of choices to make, right? Caching things, should I cache this or cache that? What should I evict from the cache? Routing, should I send it to this replica of a service or to that one? All kinds of different things. And even UI things like, should I show the user this tip fourth time, or have they already kind of dismissed it enough that I shouldn't show it to them fourth time? Should I show this in blue or red or whatever? Lots of kinds of things like that. As one example of a fairly low-level system decision to make, in C++, a memory allocator has a decision about which page of memory should it put an object that's going to be allocated. And once an object is placed, because C++ has all these crazy pointers and can't actually move objects around, you then pin that page of memory to be sort of required to be allocated and mapped in your TLB and stuff like that until all the objects on the page go away. So it's really nice if you can put all objects with the same lifetime on the same page, so that when they're more likely to not have this fragmentation problem where one object is keeping alive a whole page of memory. So stack traces turn out to be pretty good predictors of object lifetimes. So you can have a stack trace, and from that it turns out you can then do a fairly good prediction of, is that object going to live for just a millisecond or like less than 100 milliseconds? Three different sort of age buckets, where the age buckets the actual bracket of time defined by the age bucket might vary by program, but roughly small, medium, and long-term objects. And so you can actually use this and decide, based on that stack trace, which of the lifetime buckets this object is likely to be in, and then use perhaps a different page to put that object on. And so essentially you can create a model of this using the stack trace as input and make a prediction. Because that model might be a little bit expensive, you might actually want to just have a hash-based representation of the stack trace and then use that in a cache, and then you periodically discard cache entries. So this all kind of works, and you can actually get pretty significant reductions in memory usage for a program if you use this compared to a sort of an allocator that's unaware of this. And so it can, in this particular case, reduce the steady state fragmentation by 43% in this particular program, compared to the baseline allocator, which is already a fairly well-tuned thing. Okay, so learning can help you deep kind of in the guts of these computer systems. If we can make choices like this, it's going to be good. But it's actually reasonably hard to do something like what I just described in those last few slides. And so if we can make this really, really easy, that's going to be good. So we've been working on a system called Smart Choices. This is a collaboration with, again, a number of people, which is a system to help us make learned choices like the ones I just described in computer systems. We didn't actually use Smart Choices for the previous example, but it is indicative of the kinds of things we're targeting. So normally what happens in computer systems is you gather some data or have some intuitions about a choice that you're going to make, and then you update the decision rule, or you implement some heuristic that you think represents the right kinds of trade-offs for making that decision. But what we'd like to do is to be able to use data and then either kind of fairly simple contextual bandits models or maybe sort of RL-based models that can then, in a direct feedback loop, try to make better decisions for all these kinds of learned policies. And there's a bunch of challenges. So one is the usual explore-exploit trade-off that happens in sort of online learning systems where you are unsure about the ultimate reward. Non-stationarity in computer systems is also a big concern, especially for some of our operations folks. If you're running a system, it's kind of bad if it suddenly starts to behave in a very different way because the way in which the system is being used doesn't perform well. And so for some kinds of problems, the old heuristic may not have been as good, but may have more predictable performance. So we want to be able to sort of give perhaps some degrees of freedom to the choices that get made, but constrain the system so that it operates within environments where it's unlikely to plunge below the old case, the old heuristic. So as one case study, we've been working with the Google Flights team on a particular application of this. Google Flights is actually pretty complicated. When you say you want to go from San Francisco to Mauritius, which would be nice, then it actually has to do a fairly comprehensive search of all possible paths between these two city pairs, and that can take highly varying amounts of time. And so one of the things we want to be able to do is to decide what level of parallelism to use for this search so that we can sort of fairly extensively explore the set of possible paths and flight segments in a reasonable amount of time related to the latency budget we want to allocate for this. And so one of the things we've been able to do is reduce the latency by 30 milliseconds with basically no increase in CPU by making this choice a learned choice. And I'll show you the code that does that. So choosing a thread pool size for Google Flights, basically you say, I would like to get a thread pool choice object. Then we have features that are available when we're going to make this decision. And these are typically defined with protocol buffers. So in this case, we have a source zone and a destination zone for where the flights, the source city and destination city originate. Now, this is not something you would hand code in a heuristic. You'd say if source zone equals 3 and destination zone equals 5, then thread pool size equals 8. That wouldn't make sense, but a learned policy can actually take advantage of this and actually learn this relatively straightforwardly in an online matter. And then you can say, please choose my thread pool size given these input features. And then do something with that chosen thread pool size, and then give some feedback. In this case, feedback about the latency of the actual search. And so how do you actually deploy such things? The simplest configuration is you just have a local in-process system that's making decisions and updating models locally from in-memory results of rewards that are given to it. A more complex setting is you have a whole bunch of different binaries that are making choices and maybe other binaries that see the reward downstream, and you have to be able to then sort of collect and aggregate that data together, join it together, and make decisions, and then maybe have some background training process that is creating new models and then pushing those out to the client binaries. Those client binaries can then either just use the frozen trained model that is updated periodically from the centralized service, or they can also do fine-tuning on the model as they go. So the goal here is really, can we shift how we view machine learning in systems and products by making a programming model that makes it really, really easy to drop in a learned choice into the middle of some kind of fairly large existing code base of C++ code or whatever, in order to make things like the choice of thread pool size or which lifetime object bucket this object is likely to fall in. So in conclusion, I think there's lots and lots of potential for machine learning to make a big difference when applied to computer systems problems. We started out doing work in device placement, which I think is cool. I think that led to the ASIC device place and route work. I think there's a lot of opportunity for these other kind of more abstract software interfaces to make this a lot simpler than it is today. So with that, thank you. I'll take questions.
Cool. So we have time for a few questions.
Hi, thank you for the talk. I want to ask a question about the generalizability of your RL policy. So you mentioned that you train on other tasks and fine-tune on your task, but is there any hope that you can just run your policy without fine-tuning on the task you're interested in?
Yeah, you mean in particular for the ASIC placement?
For example.
I thought I had a graph of that, but maybe that's the graph that didn't show up. That's this graph. Sadly. But you can get a sense of it from this graph as well, right? So if you just do zero shot, that's the kind of pinker bar, and this bar is what happens if you do fine tuning. So in most cases you see you get a little bit of gain, but just doing zero shot training from the policy you've trained on other kinds of examples that are not this one gives you most of the benefit. And I think that's also true in the ASIC placement as well. Sure.
Thanks for the great talk. How do you think using learning in systems will affect troubleshooting or evolvability of these systems?
Yeah, I mean, I think this is one of the worries as you start to do more of this, and you maybe have multiple interacting decisions that you're making, perhaps independently or perhaps in a chained manner, where you get a reward sort of at the end of a bunch of decisions. It is going to be harder to understand. I think the interpretability of these models is important. I think if you stick to fairly simple models, often you can get pretty far with fairly simple models that are actually reasonably well understandable. And for more sophisticated applications, you're going to have more, fancier models that are going to also have, important interpretability guarantees. We've sort of just been working through the first initial users of this, and we still don't have a lot of experience with it, but we know it's important. Our operations people are particularly excited about these kinds of discussions.
Hi, thanks for the great talk. A question for those inspired with this problem of designing ASICs and similar stuff. Is there any open sourced environments or simulators to try to reproduce and play around with this? And is there anything publicly available, including this research?
Yes, we are working on some open sourcing of this kind of work. Stay tuned.
Okay, I'll catch you later.
Yeah, talk to Anna and Azalea.
Okay, I think we have time for one more.
Thanks for the talk. For the ASIC design, do you use a single level policy, or do you have policies at different system level granularity?
So generally what we're doing is placing a large block, which ASIC designers already think in terms of. So you might have one team that's doing this kind of block and another team that's doing this kind of block. And so those are sort of the natural interfaces. Mm-hmm. And then for a large chip, we'll place the blocks and then take the size and areas of those blocks and do another level of placement. But for smaller chips, you can just do the entire thing as a single computation.
Thank you.
All right. Thank you.
Thanks.